Reasoning without the right context is just expensive hallucination. Look, if you're diving into building AI agents, you've probably already run into the exact pattern that absolutely kills most production deployments. Our underlying models, they've gotten incredible at reasoning. But if you just drop a stateless large language model into a production environment, it completely falls apart. It can't remember what it did yesterday, it totally loses track of its current goal, and it just repeats the exact same mistakes over and over again.
So, welcome to this explainer on Module 12, End-to-End Projects. Today, we're really focusing on how to integrate all those core AI concepts we've talked about, like LLMs, RAG, memory, tools, and multi-agent orchestration into actual, deployable, real-world agentic systems. We're going to break down the exact memory architecture you need to make these agents function seamlessly out in the wild.
Okay, here's our roadmap for today. We'll start with the AI amnesia problem, then look at the 4 types of agent memory, architecting hierarchical memory, knowledge graphs and factuality, consolidating lifelong learning, and finally, building end-to-end agents. Let's get right into it.
Starting off with Section 1, the AI amnesia problem, and exactly why production agents fail without a proper memory substrate.
It's the million-dollar question, right? Why do basic vector storage architectures completely collapse when you try to scale them past simple, one-shot queries? When an agent has to, say, maintain a conversation across hundreds of turns, or coordinate with other agents, or build up context spanning weeks, just dumping everything into a flat vector database simply does not work.
And that's because these flat vector databases can't tell the difference between what is merely semantically similar and what is actually relevant. This leads to 4 massive failure modes. First up, context poisoning. If your agent hallucinates and then stores that error, it's going to retrieve its own mistake later, and the failure just spirals. Next is context distraction. Imagine your vector search returns 10 things that sound similar, effectively burying the one critical piece of info under a mountain of noise. Then we have context clash. This is when contradictory facts load at the exact same time, like pulling up an old shipping address and a new one simultaneously, which just destroys the agent's coherence. And finally, work duplication. In multi-agent systems where they don't share memory, they end up burning expensive compute doing the exact same redundant tasks.
Which brings us to Section 2, 4 types of agent memory, where we map human cognitive science directly to artificial intelligence.
So the huge takeaway here is that we absolutely cannot treat all memory as the same thing. There are 4 distinct types we have to handle. Working memory is your agent's active workspace. That's the LLM's context window holding immediate variables, like active RAM. Then you have episodic memory, which stores specific past experiences so the agent can preserve a timeline and actually know who it talked to yesterday. Semantic memory stores persistent, verifiable facts about the world, usually in a knowledge graph. And lastly, procedural memory. This is basically the muscle memory. It encodes validated tool use and executable code. By separating these out, your agent can maintain its train of thought, verify facts, and execute complex skills without getting totally confused. All right, moving to Section 3, architecting hierarchical memory and using the operating system analogy for context management.
Let's really contrast the clunkiness of flat vector storage with the elegance of hierarchical memory. Flat storage just runs these broad similarity searches across millions of entries, which guarantees massive token bloat and context distraction. But hierarchical memory, which you'll see in advanced architectures like HMEM and MEMGPT, organizes data into strict layers like domain, then category, then trace. It literally acts like a computer's operating system. The agent dynamically pages information in and out of its active context window. It only pulls from disk storage what it desperately needs for active RAM, which saves a massive amount of compute and tokens.
Think of the AMEM, or Agentic Memory Architecture, kind of like a wildly smart, interconnected note-taking system inspired by the Zettelkasten method. When this agent interacts with the world, it doesn't just blindly log raw text. It constructs a highly structured atomic note, packed with context, keywords, and tags. And then, and this is the cool part, it dynamically generates links to historical memories based on shared attributes. So the memory network continuously evolves and refines its understanding over time, building this deeply interconnected knowledge graph without needing any rigid, predefined rules.
We really have to keep the raw mechanics in mind here. Tokenizing and embedding memory is incredibly computationally expensive. Every single time memory is inserted or retrieved, you're paying for it in processing power and latency. So, if an agent has to constantly embed and search a massive, totally unorganized database every time it cycles through an observe plan act loop, the system is going to grind to a halt. This is exactly why routing information hierarchically isn't just a nice to have. It's absolutely essential for maintaining high-speed agentic loops.
That leads us perfectly into Section 4, knowledge graphs and factuality. What do we do when fuzzy vector math just isn't enough?
Well, in high-stakes scenarios, think medical diagnoses or legal document generation, fuzzy semantic math simply doesn't cut it. You have to use GraphRag. GraphRag enables what we call multi-hop reasoning by enforcing strict structural relationships with explicit nodes and edges. Instead of an agent just grabbing a piece of data because the words kind of sort of look similar, it traverses an explainable, exact factual chain. It can logically verify, okay, patient A is on drug Z, and drug Z has a negative interaction with drug X, therefore I must recommend an alternative. It gives you the strict, verifiable factual grounding that basic vectors fundamentally cannot provide.
Let's jump to Section 5, Consolidating Lifelong Learning, where we evolve raw data into hardened rules. This is where things get genuinely fascinating. We're talking about a biologically inspired framework called active dreaming memory. It works in 3 phases. First is the wake phase. The agent is online, attempting tasks, and just generating raw episodic traces of its wins and losses. Then comes the sleep phase. The system literally goes offline, clusters all those raw episodic traces, and reflects on its failure patterns. Finally, in rule generation, the agent abstracts those clustered failures into verified, hardened semantic rules, locking them permanently into its long-term procedural memory. To put that into perspective, imagine an agent failing repeatedly with an HTTP 403 authorization error. During the sleep phase, it clusters all those raw errors together into an off cluster. It reflects on why it's failing, and it generates a new rule. Always add an off header. The very next time the agent tries to hit that API, it retrieves this newly hardened procedural rule, includes the header, and succeeds on the first try. It is literally translating raw, messy errors into permanent, reusable skills. And the empirical data proves this works incredibly well. When tested across complex domains like SQL generation, Python scripting, and API integration, agents equipped with this active dreaming memory hit near 100% success rates. This consolidation mechanism completely blows baseline models and standard RAG setups out of the water.
Finally, let's bring the whole shebang together in Section 6, Building End-to-End Agents and Deploying Real-World Agentic Systems. If you only take away one single thing from this entire explainer, let it be this. Memory isn't just a cool feature you tack on at the end of your sprint. It is the foundational substrate required to orchestrate LLMs and tools effectively. It is the core difference between a neat weekend demo and a reliable production-grade system.
A brilliant end-to-end example of this is the Voyager agent. Voyager is an embodied agent that literally conquers the game of Minecraft entirely without human intervention. How? By building a massive, ever-growing procedural skill library. When it learns how to mine a diamond, it writes the executable code and saves it as procedural memory. Using iterative prompting, it takes in environmental feedback, self-verifies its actions, and queries black box LLMs like GPT-4 to continuously adapt to an immensely complex environment without needing to retrain the underlying model. And out in the enterprise world, this exact same memory substrate is what powers serious deployments. You have customer support bots using episodic memory, so they remember a conversation from 3 weeks ago and don't ask you to repeat yourself. You've got personal knowledge management systems using layered context stacks to instantly bridge your Notion docs, Slack messages, and PDFs. And in multi-agent orchestration, they use distributed memory architectures like CRDTs, which basically just keep distributed data perfectly synced to ensure specialized subagents are always on the same page, eliminating costly, redundant work entirely. So once you make the leap from running basic stateless scripts to deploying agents equipped with genuine, hierarchical, lifelong memory, you aren't just automating tasks anymore. You are actually building synthetic colleagues. I'll leave you to ponder this. If your agent can learn from its mistakes, dream offline to consolidated skills, and perfectly remember the context of every single interaction, what will it build tomorrow? Thanks for tuning into this explainer, and I'll catch you next time.